Why isn't every matrix diagonalizable? Well, let's take a look at this A, which is 0, 1, 0, 0, and then A squared is actually just the zero matrix. So if this were diagonalizable, then we could write it as some diagonal matrix D, which is a conjugation of A. So P, A, P inverse for some invertible matrix P. Okay, but that means that D squared is PA P inverse times PA P inverse. Okay, but canceling off the P inverse P in the middle, it just leaves us with P times A squared times P inverse. But we saw above that A squared is just zero. So in other words, D squared has to be zero. But since D is a diagonal matrix, that actually forces D itself to be zero. Okay, that's interesting. But D was acquired by diagonalizing A. So we can multiply on the left by P inverse and on the right by P and conclude that A itself is zero. But that's a contradiction because A had a 1 in it originally. So this is something called a nilpotent operator. And it acts by annihilating its kernel, like any matrix. But you can also see that, in fact, the range of A is equal to the kernel. So it sets up all the other vectors to be annihilated next. Diagonalizable matrices or diagonal matrices cannot do this. It can only scale vectors in a range. Understanding these nilpotent operators helps to break into Jordan normal forms and stuff like that.